Hello there. So as part of this video, what we are going to do is establish some base or in terms of, being able to reason about things. So we'll establish some facts, some mental models on which we can kind of, base the concepts that are to come in future. So what are we going to talk about? We are going to talk about, mental models and mental models of what, CPU and system, right? So, and our intention, of course, is to head towards understanding the M class processor in a way that we can program it in assembly. All right. So, what is a CPU really? Right? What does a CPU do? So, when one can say it's like a bunch of transistors, this, that, go to that level of abstraction, or one could reason the following way. So let's assume you have a system, an embedded system, of course, that can go from state S1 to S2 to S3. So there are like three states, and it can jump from like one state to another, to backwards or whatever. Depending on what the input is or the current state is, it can take a decision as to jumping to the next state. The question to ask is who drives these states? And in an if you had infinite money and infinite engineering capabilities, you would say everything can be done as digital design, and it could be a hardware. It could be a hardware that is sensing the input, checking which state we are in, and then taking a jump to the next state, which is fine. But in most embedded systems, you can consider S1, S2, S3 to be the states of that embedded system, and we can imagine traffic light. Traffic light is simple, right, to imagine. So we go from like the red color to yellow color to green color, and then we kind of jump like so, right? So the idea then is that there are three states here, red, yellow, and green, and the system is going to jump from one to another. There is like a time component involved, and the jump also depends on which state the system is currently in. Now, the question we are trying to explore now is who drives these transitions? One answer was like a pure hardware, but that kind of depends on engineering capabilities and time. So one of the things that people tend to do, designers tend to do, is to throw in a CPU instead of this hardware. And why throw a CPU? Because once you have a CPU, you can program that CPU. So if something goes wrong, you can change the program for that CPU, and you can kind of fix the errors that your system was doing, let's say. Um, all right. So the idea then is that CPU is that entity which will kind of CPU. So it will look at inputs, and it will keep track of which state we are currently in, and then it will give some output, and then this output is essentially in ways that it changes the state of the system. For example, we were on the red lamp or the red light, and then the CPU kind of waited 60 seconds, let's say, and then after 60 seconds it figured out, hey, I'm in like the red state, this entire system is in red state, 60 seconds have passed, and now what I must do is I must turn the red light off and turn the yellow light on. So turning on and off the yellow and red lights is the output. The 60 seconds related something is input, and also the fact that it was initially red, that's also an input. So CPU then is this entity in embedded system that kind of drives the system from one state to another. And how does it do so? It does so by reading the inputs, reading the code, executing the code, manipulating the data, and driving the state. And let's quickly recap. So um, this CPU needed to know how to go from red to yellow to green. That part is instructions, right? And also called obviously code. So the CPU needs to consume code from somewhere. The second part was that it had to sense some inputs. Is it red? Has the timer expired? Has 60 seconds passed? So there is some input. And the other thing that the CPU needs to do is keep track of the state of the system, which it does so by kind of keeping, let's say, a table or some sort of information in the memory. So it needs to keep track of where the system is right now. It needs to keep track of what all inputs are coming in. It needs to also toggle the output, and also it needs to consume instructions. So it needs to, again, as a recap, instructions, data, input, output. These are the four things that the CPU is involved with. And if there is anything from this video that you should be taking, it is exactly this one diagram, right? And that is so far. So I'm going to now expand this out a little bit. So we talked about the CPU somewhat, and now I'm going to draw a diagram that is a generic system representation that will help you all across reason about systems. Anytime you're reasoning about a system with a CPU, this holds good. So there is a CPU, and then somewhere there has to be a memory. And in that memory, there would be instructions and there would be data, right? And what this CPU has to do is it needs to go and fetch the instructions. So I'm going to draw two lines with a slash on that. What these are buses. These are called buses. You can think of them as multiple wires. A bus is multiple wires. A single wire is, well, a wire. All right. So this is a wire going from left to right, and this is a bus going from left to right. And bus is multiple wires. If you see something like this, it's an 8-bit bus, meaning 8 wires together. If you see this, it's 18-bit. So we don't care about the width of the bus, so to speak. This is called the width. We don't care about that right now. So these are just buses. And I'm going to call it instruction buses because there is like some information that is given to the memory saying I need an instruction from location 0. So this upper one is called the address bus, right? And the bottom one, you can call it as instruction. These together are called the instruction buses, pair. There's an address going to the memory, and then the memory responds back with the instruction, the bits that convey the instruction, and that comes on this bus, so to speak, the second one. Similarly, the CPU might want to fetch data, and it might actually fetch data, and in certain cases the CPU might actually have an answer that it wants to save to the memory. So this is bidirectional, so it can do read and write. Write is updating the memory, read is reading, fetching from the memory. And these two buses together are called the data buses. And then the upper bus here is called again the data address bus, and the lower one is called the data bus. And the address kind of corresponds to the location in the memory that you want to fetch or manipulate the data. All right, so this was the path of CPU communicating with the memory. The other thing we said was input and output. So this is what the CPU is. This is like a model, and this is kind of a good model of a system with one change, one change that we need to add in. So recall what the CPU would do is fetch instruction after instruction and then go on executing it in a linear fashion. And what it does is it fetches an instruction first, then based on that instruction, it can either go and fetch some data so that the instruction can operate on that data. For example, if you have add, some R1, R2, #1. So it's more like, or something like so. And of course, I haven't discussed the details of the syntax yet, so don't worry about it. It's most likely also wrong syntax, but the idea is that maybe we are trying to add data that is stored in certain location with the value 1 and then somehow kind of, retain it within the CPU. That's what this instruction hints at. The idea is we want to manipulate data in the memory, and the instruction might convey that intention that, hey, I am a load instruction, go to this location in the memory and fetch the value at X address. So, long story short, the CPU is essentially executing instruction after instruction. Now, what happens if you want to add in interaction with the external world? Well, of course, we have input and output, but what if you want the CPU to attend to some input? So one of the ways to do so is that your instructions suggest to the CPU that, hey, go see if there is any input, right? That's one of the ways that in the instructions you write down after you have computed or calculated so many things, after you have done executed 5 lines instructions, go check if input has something for you to do, right? That's one of the ways. The second way is we would want to provide a way in which the state of a hardware line that is exposed to the user, so input and output kind of comes out of the system here, right? So we say that, okay, there has to be something which is input, but the state of that input, if this goes from, let's say, 0 to 1 or 1 to 0, depending on what state this line or wire is on, we would want the CPU to abandon what it is doing. And this is absolutely key. We would want the CPU to abandon whatever it is doing right now, fetch some other instructions, execute those, and those are like, let's say 20 instructions or some finite instructions. We would want it to execute finite instructions, then come back here and continue with its original operation. This is very important, and this, what I explained here, is the idea of interrupts, that the CPU was executing something, but then an external line hinted to the CPU that, hey, CPU, pause whatever you're doing, whatever you were doing here, stop that, somehow save it, do something with it, but please start to fetch instructions that are stored at some very specific location. Execute all of that program first, and after you have executed that, please return back to whatever you were doing. So this code here that we jump to, that the CPU decided to jump to in an attempt to kind of, deal with this external state, this external wire state, this is called ISR, interrupt subroutine. And this is very common. This completes our system. So system has like a CPU, memory, and in this case, I have separated instructions and data. They can be together also. I'm noting them here differently. Then there are separate buses, but then a way to communicate with the memory is what that is representing. Then you have input, output, and you have the interrupts, right? So that is what the system comes down to. Any system has these, right? So you have the CPU, and I'll kind of do this and call it IO. So you have the CPU doing IO, then you have the CPU connected to memory, and then you have interrupts. So that's that. This kind of is a complete model of a system. If you think about any system, any embedded system in these terms, you're fine. You will be fine, right? Okay, so if you have been able to follow along so far, what I want to do is briefly show you the M-class controller or M-class CPU based system. What to think when you're kind of talking about the M-class CPU. And what I have on the screen here is this document M-class for beginners, and it'll kind of be in the resources section of this course. But what you see here is this M-class CPU, right? It says this, and again, this entire arrow here is same as a bus. This is same as a bus, multiple wires essentially, right? So what you see here is pretty much the expanded view. So think of this much to be the CPU really from the diagram that we saw here. So the CPU is this much part. These are the interrupts, and interrupts can be many, right? And then there is also one interrupt from here. And what you see at this point is a bus manager called the interconnect, right? It connects multiple wires together. And so one set of wires here is going towards external things, and you can think the memory is here, right? So down here is the memory, there is CPU here, some external stuff here, some external LED switches, all of that here, and they are kind of, connected. And we'll come to the internals, in the next video, we'll talk a little bit more about that. But let me just hint at what is what. So this is the CPU, the M-class processor. This is the interconnect, so to speak. You can think of this as two railway tracks or three railway tracks, and the interconnect is essentially connecting those tracks with each other, depending on who wants to talk to whom. Very simple kind of, description. All right, the memory lives here. Now, what you see inside, that is what we'll come to as part of the next video and discuss more about this model. But what I would nudge you is please do remember this as the model of system, how to think about system. Remember this diagram, and then how to kind of the functions of the CPU are here. And we'll go into how programmers should think of CPU, write code for it, so on and so forth in the coming videos.